So, welcome everybody to this afternoon session. So, this afternoon we have two talks, and the first one will be given by Leah Santos from Yeshiva University in New York. So, it's a good continuation after the morning talk given by Guillaume on random matrix theory. So Leah will tell us about random matrices in real system and related to many-body quantum dynamics. So please, Leah, so you have 90 minutes, and so thank you
All right.
for giving this talk.
Okay, so thank you all for showing up. I also thank the organizers for this invitation. And so some of the things that I'll talk about today, and actually some of the topics that were covered by this school, they were also discussed in another Lesuche school, a school from 1989. So it was a school about quantum chaos. And well, the proceedings, they are available. And it's beautiful to see because then you get the lectures by Bo Higgins, talking about level statistics, quantum classical correspondence, Chirikov, talking about the evolution of chaotic quantum systems, Heller, quantum scars, all the students by Chirikov, Israelev, Shepelyansky, Kazati, talking about dynamic localization. So it's fascinating to see that these topics are still so much alive, although of course the resources to study them are incredible, and there has been a lot of development, but it's a beautiful proceeding to have a look at. Okay, so this lecture will be divided in basically two parts. The first part will be about random matrices, not just full random matrices. I'll also mention the Wigner band random matrices, Power-Law band random matrices, the two-body random ensembles, which is what some people now call SYK model. But the emphasis will be really on the full random matrices, talk about level statistics, although you already heard a lot about this in the morning, eigenstates, and then focus on dynamics, especially on the survival probability. And then what we are going to do, move to realistic systems. So we are going to compare the results from full random matrices with results from realistic systems, and we are going to focus on spin models, especially spin half models in one dimension. So starting again with eigenvalues, eigenstates, and then move to the dynamics. So then we'll discuss the different time scales, the different behaviors that we find as we move towards equilibration, and how long it takes for these many body quantum systems, which are isolated, to finally reach equilibrium. So we start discussing systems that are in the chaotic domain, and then move them towards localization. I doubt I'll cover everything, but at least the idea is here and the notes will be available. Okay, so let's start with the eigenvalues from random matrices. I'm going to focus only on random matrices that come from Gaussian orthogonal ensembles. So these are matrices that are real and symmetric. Now you've heard about the others in Guillaume's talk. Why? Because I want to compare the results with realistic systems. And the realistic systems that we'll be talking about are described by matrices that are real and symmetric. Okay, so these random matrices, they were much used by Wigner back in the 50s to try to describe statistically the spectra of heavy nuclei. So instead of going for all the details of this system, this complicated system, I'll just fill the matrix with random numbers. And make sure you satisfy the symmetries of the system the real system you're trying to describe. So how do you get a random matrix? Well, first think about matrices that are large, more than 1,000. So, and then you pick 1,000 by 1,000 numbers from a Gaussian distribution with mean 0 and variance 1. So we construct like this our matrix M. Add by its transpose, divide by 2, and there you are. We have our random matrix from a Gaussian orthogonal ensemble. Now, mean 0, the second moment of the diagonal 1, and of the off-diagonal half. All right, so we got the matrix. What we are going to do now, so this is your first exercise. Diagonalize it. Diagonalize it, and then collect all these eigenvalues, make a histogram, and you will see the famous semicircle shape. You can also put on top of this, of your distribution, this equation here. which is the analytical expression. And you will see very good agreement, even though this expression is obtained for when the dimension goes to infinity. But since our matrix is large, you will see good agreement. If you want to see the exact expressions for finite dimension, then you can go to Meta's book. I know Guillaume also mentioned this book to you. Yeah. So this is our first exercise. Second thing, what can you do with all these eigenvalues that you already got? Well, how about having a look at the level spacing distribution? Get all of the spacings between neighboring levels, E2 minus E1, E3 minus E2, collect all of these spacings, make a histogram with them, and you're going to get the famous Wigner-Dyson distribution. What is special about the Wigner-Dyson distribution? It's telling us that there is no spacing zero, so no degeneracies. The levels, they hate each other, no? They repel each other. They are correlated, the spectrum is rigid. You already heard in Guillaume's talk that to get this, you have to unfold the spectrum. And people usually try to avoid unfolding the spectrum, dealing, for example, with the ratio of consecutive levels, level spacing. But let me tell you a trick about how to unfold it super easy. You don't need to think much, just if you ever need to do a quick unfolding. So what is the idea? Discard the levels at the edges, okay? Because that's the region where there is too much fluctuation. Discard like 10% at the edge. And then you have the remaining eigenvalues. Then break this list of eigenvalues, partition them in some small sets, in some small groups of 10 eigenvalues, for example. Here I'm going to show you an example with 5, but do it with 10 or 11, something like that. 5 is too small. But then you just focus on this small set and get the mean level spacing. So S1 plus S2 plus S3 plus S4 divided by 4, which is just E5 minus E1 divided by 4. And then pick these spacings and divide by this mean level spacing. And that's it. So do this for all of your little sets, and you'll get a good Wigner-Dyson distribution. This works well if you just want to check, do I have a Wigner-Dyson or not? Okay, so that's the trick, and you can check if it works. All right, so this is the story about these matrices filled with random numbers. And the fascinating thing is that this simple idea works so well. This is data from a real heavy nucleus, and you see there very good agreement. So the idea was so successful, it was extended to other complex systems, atoms, molecules. You will see our spin systems showing these distributions. Guillaume told you about the Bose-Hubbard model, right? You get this Wigner-Dyson distribution. Up to now, I didn't say anything about chaos. No? I just talked about spectrum level statistics. Where does this story about chaos come from? It comes in a different context in the studies of billiards. What people noticed studying billiards was that when the billiard in the classical limit was chaotic, and now we are talking about chaos in the classical sense, Lyapunov exponent, positive, mixing, then in the quantum domain, the eigenvalues would follow the Wigner-Dyson distribution. While when the system in the classical limit was not chaotic, then in the quantum domain, you don't get the Wigner-Dyson distribution, you get something else, for example, Poisson. So this is this correspondence between level statistics and classical chaos. Now, so that's what we call quantum chaos. These signatures, these properties that you find in the quantum domain that will tell you whether you have chaos in the classical limit. This is well established for systems with few degrees of freedom. This is what Bohigan's lecture is about in this Lesuche school that I mentioned to you. So this is something that goes back to the beginning of the 80s. There is a paper by Casati about it also. It's well established for systems with few degrees of freedom because for these ones, you get the semi-classical limit. For the systems that we are interested in, systems with many interacting parts, because then it gets really hard to do the semi-classical limit. There are people trying to do this, Thomas Good, Klaus Richter, but it's not easy. So it's not well established yet. What we are going to be doing in this lecture is, I'm just going to focus on the quantum domain. So I'm just going to be studying quantum systems. And if I see the Wigner-Dyson, if it's a robust Wigner-Dyson that doesn't disappear if I change the parameters, doesn't disappear if I increase the system size, if a robust Wigner Dyson, then I'll say that my system is chaotic, okay? But you see that this is something, an open question. All right, so we talked about level spacing distribution. You've heard a lot about the ratio of consecutive levels, but these things, they detect short range correlations. Now it's space in between neighboring levels. If you want to do a complete, a detailed analysis of the spectrum, you should look for quantities that detect also long-range correlations, such as the level number variance. So the equation for the level number variance is here. It's just the variance of the number of levels, the number of eigenvalues that we have within an interval L. So let me tell you how to do that, and that's another exercise you can try. You discarded your levels at the edges. Now you unfolded the spectrum, and now I hope you did it well, as Guillaume taught you, because now we are studying long range, so proper unfold. And then what do you do with the eigenvalues, unfolded eigenvalues? Partition this spectrum in intervals of length L, and then count on each interval, how many levels do we have? So each interval you may have a different number. So you have a distribution of numbers. I'll get the variance. This will be the level number variance. And you do this for different lengths. What are you going to get? So this is another exercise for you to try, okay? What you're going to get, if these levels are uncorrelated, like when you have Poisson distribution, as you increase that interval, the level number variance just grows linearly. Okay? Now, when they are correlated, the variance doesn't grow so fast. It grows slowly, following a logarithm. In the case of the GOE, this is the expression, analytical expression for the growth of the level number variance. Okay, so you can check that as well. Okay, why it's important to do a careful analysis of this spectrum? Well, it depends, of course, of the questions that you asked. But just to show you an example, here we have a model of hardcore bosons. This Hamiltonian becomes chaotic as this T prime grows. Okay, so you see here when T prime is 0.16, even 0.08, it looks like we have some good Wigner Dyson. But if you look at the level number variance, well, 0.16 is here, no? 0.08 is here. So you see the spectrum is not that rigid yet. It's not that close to random matrices yet. We have to go to 0.48, 0.64 to get at that point. Okay. All right. So this is a quick discussion about eigenvalues. I know you heard a lot about it already. So let's move now to the eigenstates. You diagonalize your matrix, so you also have the eigenstates. The eigenstates of these full random matrices, all of them are just random vectors, huge superpositions where all of these coefficients, they are just random numbers from a Gaussian distribution. You can check that they would satisfy a Gaussian distribution. Of course, these eigenstates are normalized, and they follow this Gaussian distribution. The weights, the absolute value square, follows what is known as Porter-Thomas distribution. So just random vectors. What else can we do with these random vectors? You could, for example, compute entropies, any of the Renyi entropies, with those coefficients from your random vector. The Shannon entropy or the second order Renyi entropy. The exponential of this entropy, the exponential of the second order Renyi entropy, you get rid of the log, what you get is just this, the inverse of the sum of these components to the fourth. This is what is known as participation ratio, which is much used in studies of localization. I'm sure you've seen this before. What else could we compute? Well, the entanglement entropy. I'm going to focus just on the participation ratio here, just to show you some results. So the participation ratio, it just like the entropies as well, it helps us to know how much spread out, how much delocalized a state is. If you have a huge superposition, the participation ratio will be large because you have many, many tiny C's. If the state is localized, the participation ratio would be small. For these random vectors, what is the value of the participation ratio? Well, the eigenstates are normalized, and we said that these coefficients follow a Gaussian distribution. With this Gaussian distribution, We can get the mean, the second moment, the fourth moment. What we need is the fourth moment for the participation ratio. And so what do we get for the participation ratio? It is equal to the dimension, this D here is the dimension of the matrix, divided by 3. This 3 comes from statistics. Now, if you had G, U, E, you would get a different number here. Yeah? So, it's not equal to D, it's not equal to the whole dimension, it's dimension divided by 3. So what can you do? Do this as an exercise. You have the eigenstates. Compute all that, Porter-Thomas distribution, the entropies. What I'm showing this plot is the participation ratio for all of the eigenstates of a single realization of a random matrix that had dimension 3000. And then you see all of the numbers, no? Participation ratio for all of the eigenstates, 1000, with some small fluctuations, but they are there. It's a very boring, flat uh, figure, no? Flat curve. If you increase the dimension, you see that these fluctuations even become smaller. So it's really a line there. What else could we do? Could we compute expectation values of observables, for example, of local observables? It doesn't make much sense to do something like this in random matrices, full random matrices. Now, the basis is not well defined. Just fill the matrix with random numbers. But if you wanted to do, just for fun, pick your favorite observable and compute this expectation value. What do you think you would get? Something as boring as that, no? A line, because again, it doesn't matter with which random vector we compute this expectation value, they would all be pretty much the same. And why am I bringing this question? Okay, I heard a noise. Okay, so why am I bringing this question about observables here, even though I just said it doesn't make much sense, we don't have a basis here. Just to make a parenthesis and talk a little bit about thermalization, which is something that you heard also about. No? So how do you know if your observable will or not thermalize? You let it evolve, no? And then you have here the equation. What do we have here? These are the off-diagonal elements of the observable that we selected. These here are the components of the initial state, and these are the eigenvalues. This is when alpha and beta are different, so this is the part that controls the dynamics. This is when alpha and beta are equal, so no time dependence. If I'm doing this with full random matrices, which as we said is unphysical, but what would I get? Well, those eigenstates are just random vectors, so these numbers would be very small. When I project any kind of state into random vectors, my initial state would also be a random vector. So these components would just be random numbers and very small. And
Lea,
yes, go on.
there is a question in the chat. Is the entropy of a random vector maximal?
It's maximal in the sense that we are maximally delocalized, but just as the participation ratio, you don't get participation ratio equal to D, no? Equal to dimension. You get these 3 from the statistics. If you would look at one of the entropies, let's see, Shannon entropy, you're not going to get log of D, you get log of 0.48 D, which is just coming from these statistics. But the state, yes, it's maximally delocalized with components that are maximally uncorrelated. You could have a state where all the components are equal. This would be a state that is too much correlated, actually. So here we are talking about random matrices, so random numbers. Okay, so I continue there with the story about thermalization. So coming back, I'm doing this game unphysically with random matrices. So these off-diagonal elements are very small. I projected my initial state into random vectors. So my initial state is also random. So these coefficients here are all random numbers. And we don't have the genesis, no? It's random matrix, level repulsion. So what is this going to give us? After a short time, you see just tiny fluctuations that decrease as I increase the dimension of the matrix, no? And decrease exponentially. as we increase. So tiny fluctuations, this is what we call equilibration, this that we reach this point. Tiny fluctuations around where this term. Okay, so this is the first step in an analysis of thermalization. You have to be sure that you reach this point, that you have equilibrium, that you don't have enormous oscillations. So we equilibrated. Second step is, okay, let me now look at this infinite time average, at the saturation value, and compare it with a thermodynamic average. For example, a microcanonical average. So these O alphas here are those expectation values. So this left side, we have the expectation values and the components of the initial state. On the right is just an average over these expectation values. Okay, when will the left and right coincide? Never. No, what you want them to be close, and you want them to get closer and closer as the system size increases. So, okay, so when will they be that similar? According to ETH, what ETH would tell us, this will hold when this expectation value of this observer that you select does not fluctuate much if you compute it with one eigenstate or with another eigenstate close in energy. Yeah? So now you see what I was asking you. What are you going to get if you have compute the expectation value of an observer with random vectors? Flat, boring curve. And so all of these expectation values, if you would do it with random matrices, they're all the same. So of course, left and right coincide when you're playing with full random matrices. So it's boring. It's a trivial in this case. And so a single one coincides with the average. So that's the idea of eigenstate. You need a single one, and that coincides with the average. But as I said, it's trivial from the perspective of random matrices because you're just playing with random vectors. What becomes interesting is when you move to a realistic system. So when you move to a realistic system, the question is, how close can I get to this scenario? What kind of system will be so close to this scenario? And the answer is a chaotic system. In a chaotic system, your eigenstates are chaotic. Our initial state, if you perturb very far from equilibrium, will be chaotic, and you don't have level repulsion, so we get very close to this scenario, never equal, okay? But the idea is chaos is what ensures thermalization. Chaos is what ensures the validity of ETH. We can come back to this when we are talking about realistic systems. So this was just a parenthesis. So we talked about eigenvalues. We talked about eigenstates. I don't know if there is any other question because I see a number 2 there in the chat, but let me know. What I'm going to do now is talk about dynamics, starting with the survival probability. Okay? Dynamics under full random matrices. So what is the survival probability? It's just the overlap between the initial state and the evolved one, square. So it has different names: survival probability, return probability, fidelity between initial state and evolved one. Just don't call it Loschmidt echo, because this is very confusing when people call this Loschmidt echo. Now, the echo is something that goes and comes back. That's what people measure in NMR. So if you call this echo and you're talking to someone who does NMR, it's confusing. Yeah? So I'm going to be calling it survival probability. And I'm going to evolve this under full random matrices. It's not physical at all. Yeah, it's again that's a game that we are doing. There is no realistic system described by a matrix that is completely filled. Why we are doing this? Well, in a way, we could have asked Wigner, why you're playing with full random matrices? There, what Wigner did with full random matrices was to get analytical results. It's the same thing here. When we study dynamics with full random matrices, we can get analytical results. So this is very convenient because then, and useful, we can compare these results with what we get in realistic systems. So we can use these results to guide our studies of realistic systems, okay? But it's not physical. Okay, let's continue. What we have in mind is this idea of quench dynamics. So this is the total Hamiltonian, the Hamiltonian that describes the system that is responsible for the dynamics. And I break this Hamiltonian into two pieces. This part here is the one that determines our initial state. So our initial state is an unlit state of this part. This is the perturbation. If this was not there, there would be no evolution. So this is the perturbation that will then evolve the state. So what is this? How do we break that in the case of full random matrices? The, the diagonal part of the matrix is going to be playing the role of our H naught. And the off-diagonal elements will be the perturbation. So what is the idea? You have the whole full random matrix, you diagonalize, so each column here is an eigenstate. Our initial state is just one of these rows. Okay, so it's a simple thing. Okay, so there we go. Let's continue with the survival probability. That's the expression. I'm writing it here as a function of the components of the initial state, and the eigenvalue. So we have these phases here. It's squared. So let me open this square, and now here we have a double sum, alpha and beta. What else do I have here? This is indicating average. Okay? Average is important. We can do averages over initial states or averages over realizations of random matrices or both. And why will be clear in some minutes, okay? But averages are very important. Keep the word average in your mind. The survival probability, this equation here, is very similar.
Question. Question.
Question, yeah.
Angel, it seems to me that the separation of the full Hamiltonian into H0 plus the perturbation might not be simple or even unique, right?
If you picked a single random matrix, then the diagonal will be H naught and the off diagonal will be V. But if you pick another random matrix, then you do that separation for that other random matrix. Yeah, you don't keep the same H naught. People, you can ask again. I don't mind if it was not clear. Anyway, so here we are. This is the expression for the survival probability. And what I'm saying is that this is very similar to another quantity that people study a lot that is known as spectral form factor. So the spectral form factor is just this part of the survival probability. Yeah? So the spectral form factor contains only the eigenvalue. So the spectral form factor is used to study the spectrum, do this analysis of level statistics, but in the time domain. So this is not a real dynamical quantity. It's just analysis of the spectrum still. The survival probability is one step above that. It is a dynamical quantity because it has the components that we got from the quench dynamics. Okay, but you see that there is a big overlap between the two. I'm going to be focused on the survival probability, but many of the things that I'll tell you about the survival probability applies also for the spectral form factor. All right? Okay, so here we are with our survival probability. What I'm doing here is I separated that double sum, alpha and beta different here, and alpha and beta equal here. This part, no time dependence, right, is what we talked about already before, the saturation value, the infinite time average now of the survival probability. Now, some of these coefficients to the fourth, you've seen this before. Some of these coefficients to the fourth is what we call inverse participation ratio. Now, this is not for eigenstates, this is the inverse participation ratio for the initial state that we selected. And I'm going to use this notation with this bar. Now, since we are talking about random matrices, any state projected into random vectors is itself a random vector. So my initial state is also a random vector. So we know what the value of this saturation point is. 3 over the dimension of the matrix. So we are done with this part. Let's then focus on this first part. And this is going to be a little rough. Now, I'm not going to go into too many details, but let me just give you the main steps of this derivation. First, I'm going to write this sum as an integral. I can do that if I insert here this delta function. If I solve this delta function, you see that I go back to that sum. What else are we going to do? We have this average. But the eigenstates, the components of my initial state, are uncorrelated with the eigenvalues because these are just random numbers. So I can separate the sum of this average, the average of the components and the averages of the eigenvalues. And then let's see this. What is this average? How can I get this average for the energies? I need a probability density function. So this integral here with this probability density function. But my focus is on just two eigenvalues, so I can write this probability density function with this R2. So this R2 is a probability density function, but where we care only about E alpha and E beta. Now, it's a probability density for finding the level around E alpha and E beta. We don't care about the other levels. So these factorials are taking into account the other levels. Yeah? Now, these are two. Well, all these probability density functions, they are studied a lot in books about random matrices. No? So go to Meta's book and you'll find all this. These are two is the 2-point spectral correlation function, but they study all 1, 2, 3, 4-point spectral correlation functions. No? So it's all detailed in Meta's book. So these are two can be written in terms of two functions, the R1 and the T2. So lots of names here. No? The R1 is just the density of states, which we know is the semicircle. The T2 is the interesting one, is the two-level cluster function, doesn't matter the name. The T2 is sort of related with that level number variance that we saw before, is the part that contains the information about the correlations. No? So this part, no information about correlation, is just 1 point correlation. The T2 is the correlations between the eigenvalues. That's the most interesting part. So to solve our integral, we have to solve two parts, the one with the density of states, the one with information about the correlations. The one with the density of states is just this triple integral that we have, very simple. Look, to solve the integral in E is just a delta function, and the other two are the same, no? Apart from this sign here. So we are left with this integral to solve. So what do we have here? R1, which is density of states, and this is the Fourier transform. So this is the Fourier transform of the density of state, the Fourier transform of the semicircle. And the Fourier transform of the semicircle is a Bessel function of the first kind. So we solve the first part. The second part, which is that one that contains the information about correlations, then there are some steps there. Okay, I'm just going to tell you that this integral also has a solution, and it's this function here. I'm giving you the form of this function. This function, this B2, is known as two-level form factor. Is where all the information about correlations are. And all the information about correlation is. Yeah? So we are done. Yeah? From the eigenvalues, what we got? One part that has is the disconnected part that came from the density of states. The other part that contains information about the correlations, the saturation. We are left with these components of the initial state, but this is super simple. This is a sum when alpha and beta are different. I can write this a sum of all alphas and betas, no? And this, well, sum of all components. Sum in alpha of these components is 1, in beta is also 1, so I got 1, and I'm left with the inverse participation ratio. Okay, so we got here a whole analytical expression for the evolution of the survival probability under GOE random matrices. Think about matrices that are large. Yeah? So this is the expression, analytical. We are showing this here in this plot with this red line, and black is the numeric. So you see, very good agreement. Let's talk a little bit about each of these terms. So the first one we already said, it came from the density of states. It only cared about the envelope, the shape of this density of states. If we look at this term asymptotically, you will see that we have a power law behavior. You see, so usually you think, random matrix, super fast evolution. Yeah, initially, but then it slows down and you have this power law behavior with exponent 3. Okay. When is the B2 going to come into play? Later. The B2 is what describes this part of the evolution. The B2, the two-level form factor, is the part that describes this dip that we have below the saturation point. This dip is known as correlation hole. It's also what some people in high energy physics now call ramp, because we reach this minimum point and then we are going up on this ramp towards saturation. I think correlation hole is a more informative name. That's the name that has been used in quantum chaos. Why? Because this hole, this dip, only shows up if the eigenvalues are correlated. If you have a Poisson distribution, you're not going to see this. Okay, so this is a direct dynamical manifestation of spectral correlations. So if we are calling spectral correlations, as in this lecture, no? If we are calling spectral correlations quantum chaos, equal to quantum chaos, this is the manifestation of quantum chaos that we found in the dynamics. Short time evolution is not a direct manifestation of spectral correlations. No? Think about out of time order correlated, and I'm sure this comes to your mind. That exponential growth of the out of time order correlated detects instability, not correlations between the eigenvalues. Okay? So the correlation hole, which we get by studying the survival probability or just the spectral form factor, is a very nice way to study statistics, level statistics. Why? It detects short and long range correlations. You don't need to do any unfolding. I didn't do any unfolding here in this story. And there is another important reason, another big advantage of this correlation hole is that you don't need to separate your spectrum by symmetry sectors. I'll come back to this, okay? So my exercise for you is try to reproduce that. You're already playing with random matrix. You diagonalize it. Well, evolve the survival probability, which is such a simple quantity, and check that it matches this expression. But when you do this, then I come back to that word that I told you to keep in your mind, averages. When you do this, make sure you do averages, either over initial states, over realizations of random matrices, or both. Now, here we did, I don't know, 100 averages over realizations, I think. So averages are important. And why? If you pick a single initial state, a single matrix, you will see big fluctuations here. You cover the hole. You're not going to realize that there is a hole. Okay, so if you don't do averages, you won't know if the system has correlations or not. So why averages is important? Now I'm going to make a parenthesis to tell you about this property that is self-averaging. So self-average is a very important property when you're studying disordered systems. What does it mean? What does it mean that a quantity is self-averaging? A quantity is self-averaging when its relative variance, so the variance divided by the square of the mean. So when this relative variance decreases as the system size increases. So what does it mean? Why is it so important? If this variance, relative variance, decreases as the system size increases, that means that if I increase my system size, I can use fewer and fewer, I can reduce the number of samples that I use, either in my experiment or in our case here, our numerical experiments. And think about it, this is usually with what we all do. Now, when we are studying, for example, many-body localization, well, increase the system size. You have this enormous Hilbert space. Let me at least reduce the number of random realizations. No? But if your quantity is not self-averaging, you cannot do that. So we have a sequence of studies about self-averaging discussing that. I just showed to you one example where this is dangerous, the survival probability, not the spectral form factor. If you don't do averages, you're not going to see the whole. Yeah? Because the survival probability is not self-averaging. So this is something that we showed, again, analytically, using full random matrices. No? That's the big advantage, as I said, of these full random matrices. We can get results analytically. So we already got to the result, what's the survival probability. No? To get a result for this relative variance, it's a bit tedious, no? Because you have to compute the survival probability square. So you have to deal with these four terms there. But it's doable. Mauro Schulas did it. No? And what you find is that the survival probability is not self-averaging at any time scale, from perturbation all the way to saturation. There were some discussions already back in the 90s, many papers about it, the spectral form factor. Whether you say, oh, the spectral form factor, the region of the whole is not self-averaging. Here we are showing that it's not self-averaging anywhere. So this is interesting thing. Usually when we are thinking about is the quantity self-averaging or not, we think about critical points. Here we are saying deep in the chaotic case, the extreme case of full random matrices, and you don't have self-averaging. Yeah? Meaning you increase the dimension of your matrix, keep doing your averages, otherwise you're not going to see the whole. What I'm telling you an exercise is, well, since you already have the matrices diagonalized, compute the survival probability, you can also compute this ratio and see that as you increase the dimension of the matrix, this ratio increases instead of decrease. And at long times, the region of the hole, the region of the saturation, it's one. So no self-averaging anywhere. This part you can show analytically easy. All right, so I have another example of a danger of self-averaging, and this is a parenthesis. I told you that if you don't do big averages, you're not going to see the correlation hole. There is another region, another problem where self-averaging can give us a hard time. So you've seen this Hamiltonian before, right? The Hamiltonian that is used to study many-body localization. Everybody agrees that in these studies of many-body localization, finite size effects is a big problem. It's hard even to determine where the critical point is. It's hard to do scaling analysis. Um, there are even people questioning if there is a many-body localized point or not. So finite size effects for sure is a problem in studying many-body localization. What we brought up is, well, lack of self-averaging is another problem that we should take into account. This is something that you can check. Um, so there is one of these questions when we study many-body localization is, do we have eigenstates that are fractal before localization or not? And how do you determine if if the eigenstate is fractal or not? You do scaling analysis of the inverse participation ratio, the generalized inverse participation ratio. So this slope will tell us if the state is fractal or not. If this slope is 1, it's not fractal, it's like the random vectors, delocalized states. If this slope is between 0 and 1, then it's fractal. Okay, so this panel here is a panel deep in the chaotic regime of this model. Each symbol, you see different shapes here, each symbol is a different number of random realizations, from 100 to 30,000. They all on top. Yeah? So deep in the chaotic region, this quantity is self-averaging. It doesn't matter how many realizations we use. Now, as we start getting closer to the critical point, see the mess that this thing becomes. Yeah? So depending on the number of realizations that we use, we get different slopes here. So that's the danger that I was talking about. Once we get closer to the critical point, this quantity is not self-averaging anymore. And so this is just a message for you. Whenever you're doing the studies of special disorder systems, check that you have, check if your quantity is or not self-averaging. If it's not, well, go on putting a lot of realizations until you see convergence, okay? But this is the detour, not my parentheses. Let me come back to the dynamics on the full random matrices. So here I have another exercise for you. We already talked about the evolution of the survival probability. Well, how about evolution of the entropies that we discussed? How about the evolution of the inverse participation ratio? Here I'm not going to show results for you, but I can then share the codes with you, okay? But what do I mean by evolution of the inverse participation ratio? We just talked about participation ratio of eigenstates, something that was static. What does it mean now, evolution of inverse participation ratio? The idea is we have our initial state that is going to evolve, and now we are going to look at the overlap with each n. N here is like the basis vectors. Now, one of the n's is the initial state itself, but there are many others. So what is this quantity measuring? How this initial state spreads, no? Not just the probability to find it on itself, but how it spreads into all other basis vectors. Again, it's a bit strange to think about it in full random matrices, but let me just show you a picture of a spin system. So what is the idea? You started with a state like this, now with a many-body state like this, and step by step, it's going to visit all of these other product states. And so this IPR is the probability to find this state, is the spread of this state into all these others. Once you reach the minimum value of the IPR, that means the state spread completely in this many-body Hilbert space. Okay, so this is something that you can try, and more interesting, check if you can get some kind of analytical expressions for these quantities. Okay, so we talked a lot about full random matrices. As I told you, they are not realistic, even though they are super useful. And why they are not realistic? Think again about that matrix that I told you, the Hamiltonian that describes, that is used in studies of many-body localization. If I look at the Hamiltonian matrix in a certain basis, what do we get? Whole bunch of zeros, it's super sparse. We have non-zero elements just within a band, and even within this band we have zeros. Now we may not even have random numbers. No, there's lots of correlations between these elements. This is a realistic system, so very far from a matrix filled with random numbers. Of course, Wigner knew this very well. Wigner created what is now known as Wigner band random matrices, which are matrices that where you have random numbers, but just within a band. And you can play with the width of this band, but outside, everything is zero. What is the problem when you start going to these more realistic kinds of random matrices? It starts getting hard to get analytical results. Okay, so that's the main issue. But this is an attempt to get closer to something real. What he did in this matrix is actually the off-diagonal elements, the absolute value is just the same number, but what was run was the signs. And then people elaborated over this idea, started playing with random numbers from different kinds of distributions, added sparsity also within the band. Another kind of random matrix that is more realistic, the power law banded random matrix. So many people studied that also. So one example, this I got from Varga's paper, is this. The diagonal, no? The second moment of the diagonal is 2. The second moment of the off-diagonal elements is given by an expression like this. And then they use different kinds of expressions. Okay, I'm just showing to you an example. So what this example tells us, see, if this B here is the size of the matrix, no, then this term disappears and we are back to a full random matrix, 2 and 1. Now, if this B is small, that means that the terms, the elements out of the diagonal become very small. Yeah? So with this B, we control how far these elements go, the amplitude of these elements go out of the diagonal. Yeah. Okay. Another very realistic kind of random matrix is what is known as two-body random ensemble. So what is this? You have the one-body term with random numbers and the two-body term with random numbers. This matrix has been studied by everybody in the quantum chaos community and people in nuclear physics, no, Zelevinsky, because this is super realistic. It's two-body couplings. This is what now people sometimes call SYK model. It's the same thing, but of course, these people are asking different questions. Okay? So what is my suggestion for you? You've seen here some examples of random matrices. There are others. Pick one of them. Pick one that you like the most and try to do everything that we've done so far. density of state, level statistics, structure of the eigenstates, evolution of survival probability, inverse participation ratio. What do you get? How do things change? I'm going to show to you one example only, which will be useful for us later, okay? This is results from the power law band random matrix that I mentioned to you before. And I'm just showing the survival probability. So when this B is equal to the dimension of the matrix, that's the scenario of full random matrix. And that's what we are getting down here. These dot lines is the Bessel function that I had shown to you before. And after that, we'll get to the correlation hole. As we go on decreasing this B, we are like shrinking our matrix. And what do we see? The dynamic slows down and the power law decay slows down, the exponent decreases. And what's happening to the correlation hole is getting postponed. Keep this picture in your mind. It's going to come back. We'll see something very similar when we go and study realistic systems. So I'm going to move now to realistic systems. I don't know if I'm talking too fast. Does anyone have any question or should I continue? I give you 1, 2, 3 seconds. Okay, so I'm going to continue now, discussing now all the things that we talked before, but for a realistic system. Okay, and we'll be focusing on spin half models in one dimension. So an example of Hamiltonian is this one, where sigma Pauli matrices. This Hamiltonian, when we have just couplings between nearest neighbors in one dimension, the x and the y have the same strength, the z is different, so it's known as xz model. So this Hamiltonian is integrable, it can be solved with the Bethe ansatz. If you look at level statistics, level space and distribution, you usually get Poisson, not always, okay? Usually you get Poisson for this integrable model, but there are some special points in this Hamiltonian. One very clear special point is when this delta is 0. So you're left with the XX model. The XX model is full of degeneracies. So you're not going to get a Poisson, you get a peak. Okay, just to show to you, Poisson is not the only thing that you can get when you have an integrable model. You may also have an integrable model where the spacing now is where the eigenvalues are almost equidistant. An extreme case of that is the harmonic oscillator, when they are the spacing is exactly the same. So for integrable models like that, you don't get Poisson, you get some funny shapes. This kind of spectrum, they call it peaked fence. Not these ones where you have almost, the levels are almost equidistant. They call it peaked fence. In a peaked fence spectrum, the eigenvalues are even more correlated than what you have in random matrices. The harmonic oscillator is super correlated. They are exactly separate. The separation is exactly the same. Okay. Now let me show to you another interesting example. Let's think about the Anderson model in 1D. So you have just hopping here and the term of on-site disorder. So you know that this model is localized, no matter how small this disorder strength is. But when you're doing things numerically, you play with systems that are finite. And if you pick a system that is smaller than the localization length, well, this system doesn't know that it's localized. So you're going to get something like a Wigner-Dyson distribution. Yeah. Now, of course, if you increase the system size, then you're going to lose the Wigner-Dyson distribution. It's not robust, but that's what you get. So I give you an exercise, a simple exercise, which is fun. Pick the 1D Anderson model, yeah? Hopping and on-site disorder. So it's just a 3-diagonal matrix, very simple to create. And study level statistics as a function of this parameter C here. What is this C? The ratio between the localization length and the size of the chain, which is the same as this ratio here. This W is the strength of the disorder. No? So we study level statistics as a function of C. Pick your favorite chaos indicator and see how it changes as we increase disk C. So here I'm showing the average ratio of consecutive level spacings. Yeah. So when this ratio is very small, that means my localization length is smaller than the size of the system, you will get Poisson. But when this ratio becomes larger, so the localization length is larger than the chain, look what you're going to get as you go on increasing. You will get GOE, then GUE, GSE, peaked fence. You can get everything with this very simple system. All the symmetries show up in this very simple system. So it's not caused by symmetries here, of course. No, it's just causing by this it's finite size effect. But it's fun, I think. Anyway, coming back to our spin models. This is the integrable model. We can bring it into the chaotic domain. There are different ways to do that. For example, if I add couplings between second neighbors, either just the ZZ part, the XXYY part, everything, it breaks integrability, it becomes chaotic. So as I increase this lambda here, we'll see that we'll get out of the Poisson, it will get more and more and more deformed until we'll get to the Wigner dice. And Guillaume told you about that, the Brody distribution that you can use to see this transition. There is also an expression that Israelev created to study this transition. Okay, there are other ways to break integrability. We talked about this model with couplings between second neighbors. No? So many terms were added here, but there is even an easier way, which is this. Here's the XXZ, and you add a single defect, single impurity, a single Zeeman splitting different from the others. No? So a single site where you have this Zeeman splitting different from the others. This will give you a chaotic system. And since it's chaotic, it will also thermalize. No? It will also satisfy ETH. If you do that, just be sure you don't put this defect at the edge. If you're playing with a chain that is open, don't put the defect at the edge because it remains integral. You can put it anywhere except the edges, okay? And what is interesting, putting a little defect doesn't bring just this model into the chaotic domain. It seems to be bringing all these integrable models into the chaotic domain. This is the easy in a transverse field. This super simple model. Now you can solve it with, you don't need beta ansatz to solve this. You put a little defect and you're going to get Wigner dice. And you can play with other models. This is a spin one model. Right? To get integrable point here is more complicated. So this is the Hamiltonian. This whole thing is the Hamiltonian for spin one integral. You add a defect, it becomes chaotic. Okay, so this I leave you as an exercise to check that these models are really chaotic in the sense of level statistics. Yeah. So check that you get Wigner Dyson distribution as you go on increasing this d from 0. And then I leave you another problem, which is really an open problem. So that's an interesting thing, which is, okay, if these models show Wigner Dyson distribution, you know they thermalize, the eigenstates have structure similar to any of the other models, chaotic models. But what becomes really interesting is the study of dynamics of these systems and transport behavior. So that's my suggestion for you. Pick these models after you started, okay, it's chaotic. Try to analyze the transfer behavior. Is it diffusive? Is it ballistic? Why I'm asking that? Usually associate chaos with diffusive transport. What Marcus Rigol and John Gould showed recently is that for this model here, they didn't see diffusive behavior. They actually got ballistic behavior. No? So how about the other model? So this is really an open question, and it's something interesting, I think, to do. Okay, so I'm coming back to that model with many other terms, the couplings between second neighbors. I told you that with this one, we can get a Wigner dice, and then when this lambda is not too small, for our finite systems, we get this Wigner Dyson distribution. But a model like this, there is no disorder here. This model is full of symmetries. What are the symmetries? Parity is there. If I have half of the chain with spins pointing up and the other half with spins pointing down, we also have spin reversal. Okay, I can just rotate it by 180 degrees. Fabian, I have a question, yeah.
Yeah, just to make sure what you call parity, just inversion around the center of the chain. Is that correct? Or
parity is like if you have one here and all down, so I can reverse, put all down here and up here. No, parity is like you put a mirror.
yeah, it's a reflection around the
Reflection,
center of
yes,
the chain.
reflection,
Okay,
exactly.
okay.
Yeah, and the spin reversal is like you have.
Yes, SZ goes to minus SZ.
Yeah, okay, good. And the other symmetry that we have here is when delta is 1. When delta is 1 and the chain is isotropic, then you have a conservation of total spin. If you don't take these symmetries into account, put all these eigenvalues together, you're not going to get a Wigner-Dyson. Here it is. You get something that looks very much like a Poisson. Why? Because eigenvalues from different symmetry sectors, they have no reason to be correlated. It's like eigenvalues from different matrices, from different systems, and they have no reason to be correlated. So to get Wigner-Dyson, what you have to do, you have to take those symmetries into account, separate the eigenvalues according to the symmetry sectors, or avoid them. How can you avoid them? Well, I always avoid this point, this delta 1, the isotropic point. The other symmetries, you can take them into account, or you can put a little defect somewhere, like at the edge of the chain, and it will break these symmetries. Okay. Now, we can take the symmetries into account or break them when we know which symmetries we have. But how can we know? For this system, it was not so hard, but you may have a very complex system that you don't know much about, and you don't know what the symmetries are. And if you get a Poisson, what are you going to say? Is it chaotic? Is it not? Okay. So is there any way to detect level repulsion, to detect chaos without taking into account the symmetries? And that's what I mentioned to you before. With the spectral form factor or with the survival probability, for this model here, as I said, we have the Poisson, but if you let it evolve, if you let the survival probability evolve, you will see the hole there. Now, so the correlation hole detects chaos, even if you don't separate things by symmetry sectors. So that's what I was telling you is one of the advantages. So as I said, you don't need to do unfolding. It doesn't care about symmetries, and it detects short and long range correlations, and it's a dynamical quantity. So being dynamic is very useful, especially if you think about experiments with cold atoms, ion traps. These people don't look at spectrum, they look at dynamics. Now it's different from people in nuclear physics. They have access to the spectrum. So these are advantages of the survival probability. You may ask, but can we measure survival probability experimentally? Well, that's a good question. But there are other local quantities that will also show the correlation hole. I see a question. Artem, yeah?
Yes, so I wonder whether you would still see effects of the initial state, say. I mean, if the initial state has some definite symmetry, it cannot explore the entire Hilbert space in any case, no?
Yes, but that's the whole point. It doesn't matter which initial state you pick. What is going to happen is this saturation point will be smaller because you're not visiting the whole Hilbert space, but the eigenvalues are still correlated. So you will still get the hole there, you see? So that's the whole thing. The hole is always going to be there because no matter which sector you are in, there are correlations.
No, I mean, maybe to be more precise, but it will be a different D then in this case than the entire Hilbert space dimension. So if you want to fit your formula, let's say you would have to look which D fits or not.
It will be, okay, so this formula here, the B2, that two-level form factor that you use to fit that, yes, you will see that you're not going to use the whole dimension of the Hilbert space. It's going to be smaller. And that will tell you, okay, I have correlations, I have symmetries, and it can even help you to detect how many symmetries you have. Now, because if the saturation was 3 over D, okay, then you would say, okay, we went all the way through Hilbert space. But here, because you have symmetries, you see it's higher. And by how much higher the hole is and the saturation point is, you will say, okay, I have 2 symmetries or 4 symmetries and so on. Fabian, you have a question also?
Yeah. Actually, it's on the time scales because well, basically, well, you have several time scales in this quantity. Actually, I guess.
Yes.
You have the one which saturation that's exponentially large, I guess.
Yes.
To the end of the hole in some sense. The beginning of the hole, I actually not sure what is the time scale, or does it scale with system size?
Yes.
And related to that, I'm thinking about numerics. You need the full spectrum, right, to compute the full time dynamics.
Yes. Okay. So this is all good. The time scale, I'm looking at my watch. I'm not going to be able to tell you more. The time scales for the survival probability. Yes, the time where the hole shows up increases exponentially with the system size. It goes as the dimension to 2/3, while the saturation goes with the dimension. I can explain to you later, even if we don't have time. But, and so this could be a problem, yes. And yes, you have to do exact diagonalization because you are going at very long times. But if you study the spectral form factor, if you don't care about those components of the initial state, if you take out the one body part, then this should show up quickly. If you just look at the just the exponential of the eigenvalues, this will show up quickly. But yeah, the time scales, I can well, you will see in these notes also the story about the time scale.
Thank you very much.
Any other question? Okay, so I'm going to tell.
There
Yeah,
is,
Nicola.
I think, yeah, there is one by Edith. I'm not sure if I understood it well. I think it's about what is maybe the value of the lambda parameter in your, so the second neighbor coupling.
Okay, so this term here, it depends on the size of the system that you're playing, okay, to get chaos. If it's 1, if you have these 2 terms competing, for sure you'll have chaos. Now, what we see is that as we increase the system size, this lambda can be smaller and smaller, and you will still have good chaos. And this is a discussion that is also actually open, whether an infinitesimal value here would be enough for chaos in the thermodynamic limit. But anyway, this is getting out of the question. Huh? If you're doing things numerically, put a big value there. Big meaning close to 1, 0.6, 0.7, then you for sure will have chaos, okay? Okay, there is another way to detect correlations or to know that the system is chaotic, even despite the presence of symmetries. And this is something nice. And I think there are open questions here as well. This is what is known as off-diagonal ETH, which is just a name. Now, remember when we were talking about thermalization, you had this observable, evolving, and one of our concerns was this part here. We have to be sure that this would take us to small fluctuations. So the analysis of this part is what is usually called off-diagonal ETH. Okay. Anyway, so we said that these off-diagonal elements are very small in a chaotic system. But there is another interesting thing about them, which is Masoud discussed in his work. The distribution of these off-diagonal elements is Gaussian when the system is chaotic. If it's not, you get funny other kinds of shapes. But when it's chaotic, it's Gaussian. What we see, and here I ask you to check that also. If I have this model, well, with all those many symmetries, and I don't care about the symmetries, so I don't know about them, and I compute the off-diagonal elements of unobservable, I picked here on-site magnetization, what do I get? Again, I get the Gaussian shape, but with an additional peak. This is telling me the system is chaotic, but there are symmetries. No? So it's a nice way to find out that there are symmetries. So here you are, my exercise. Pick the model that you like with many symmetries. You see that you get a Poisson, but then look at the survival probability, look at the off-diagonal elements of an observable, and you see, no, the model is actually chaotic, but with symmetries. there are, I think, 9 things to be done on top of this idea. No? Not just as a detector of chaos, but also as a detector of symmetries, both quantities. Okay? Anyway, I talked a lot. Let me continue. Up to now, I'm just talking about level statistics. That's what the realistic systems have in common with full random matrices. But as I said, these realistic systems are far from being described by matrices filled with random numbers. So there are differences. Where do we find differences? For example, if you look at the density of states, for random matrix is the semicircle, the density of states for realistic system is Gaussian. Why Gaussian? It's Gaussian when you have many body and a few body interactions. This Gaussian shape has nothing to do with chaos, okay? This Gaussian shape is just a combinatorics. If you have just one excitation, no interactions, for a realistic system, you get a U shape. 2, you start getting a peak in the middle. 3, you smoothen the peak. Above 4 or 5, you get the Gaussian shape. And that is like central limit theorem. Nothing to do with chaos here. Okay, how about the eigenstates? There also we find differences. As we said, all of the eigenstates of full random matrix are just random vectors. In realistic systems, the story is different. There is a dependence on energy. The states close to the edges are not fully delocalized. Now, close to the edges, we do not have chaos. Chaos is close to the middle of the spectrum. So it's in the middle of the spectrum that we have things that get closer to random matrix. Never there. We always have some level of correlations. But you see, in studies of dynamics, in studies of thermalization, this energy dependence is important. It's in the middle of the spectrum that we should have thermalization, not at the edges. Yeah. Okay, let's talk a little bit also about structure of the initial state, thinking about the dynamics. We said that we are doing quench dynamics. No? So that's my initial state is determined by this part. And what can I say about the structure of this initial state? In the case of full random matrix, we say, oh, it's just another random vector. What happens in these realistic systems? So I'm picking a Hamiltonian that is chaotic, the one that is going to evolve the system. Okay, so chaotic eigenstates. I'm going to pick an initial state that has energy in the middle of the spectrum. Okay, so I'm picking an initial state that has energy here, which is the region of chaos. And I want to discuss the structure of this state. What else do I need to tell you? How strong this perturbation is. Because if this perturbation is very small, if the system is not perturbed very far from equilibrium, my initial state will be very close to one of the energy eigenstates. So it's going to be localized in the energy eigenbasis. So what I'm showing on these panels is the distribution of these components for the initial state versus the eigenvalues. So if this lambda is very small, what is the distribution? Very narrow, close to a delta function. As we increase this perturbation, you go through a Lorentzian shape. Some people call it Breit-Wigner, Cauchy. It's a Lorentzian. As you keep increasing, eventually you get a Gaussian. So it's this limit here, or strong perturbation, chaotic Hamiltonian, middle of the spectrum, is in this limit that thermalization should hold for few body observables. Coming back to that discussion. But let's then talk about survival probability in these realistic systems. This was the expression of survival probability. We wrote it in terms of the coefficients of the initial state. When we're talking about random matrices, we open this square. Now I'm not going to open this square. I keep it here, but I'm going to write this sum as an integral, where this row here is a sum of delta functions. Now that's how I recover that point. This sum of delta functions is what I was showing here. This sum of delta functions weighted by those components is the energy distribution of my initial state, what people call local density of states. So you see that, what is the survival probability? The Fourier transform of this distribution. And we already saw that for full random matrix, the density of state is semicircle. The energy distribution of the initial state is also semicircular because these coefficients are just random numbers. So Fourier transform of this semicircle gives us the Bessel decay that we already talked about. How about our realistic system? Okay, so here what we have is the Hamiltonian that is going to evolve my system is that with couplings between second neighbors, the chaotic Hamiltonian. And I'm picking as initial state an eigenstate of the XXZ model. So this is not really something that an experimentalist could do. No, it's our numerical game here. And I'm picking an initial state with energy in the middle of the spectrum. When this perturbation is very small, we have delta function. Fourier transform of that gives us a very slow decay. As I go on increasing this perturbation, Lorentzian, which Fourier transform the Lorentzian give us exponential behavior. I go on increasing this perturbation, I get a Gaussian, which gives me Fourier transform a Gaussian decay. So this gamma is the width of this distribution. Why I'm telling you all this? No, this Fourier transform is something simple, but just to show to you that this initial behavior of the survival probability is controlled by perturbation and the strength of the perturbation. There is nothing to do with chaos here. Look, and this is my next exercise for you. What I just said is initial state from the XXZ evolving with the Hamiltonian that has couplings between second neighbors. And we looked at the energy distribution of our initial state. This first plot is very ugly. No? It's close to a delta function, then Lorentzian, and then Gaussian. Do the same, but for this kind of quench, where we go from XX to XXZ. And so our initial state is the initial state from the XX part, and we let it evolve according to the XXZ. So the anisotropy is the quench parameter now. As this anisotropy increases, we get the same thing, Lorentzian, Gaussian. And if I do the Fourier transform, exponential for both cases, Gaussian for both cases. So you see, this quantity is not detecting anything about chaos. The short time dynamics only has information about how strong the perturbation is, how far we take the system out of equilibrium. No information about level statistics. Yeah? No information about chaos. The same behavior for integrable models or chaotic systems. Where does the information about level statistics come from in the dynamics? So this is related with Fabian's question. At much longer times. That's where we develop that correlation hole. And this is what I wanted to study, tell you now. And yeah, lots of things, but I don't think I'll be able to cover. But I'll studying the survival probability all the way to saturation. Now I'll start telling you a little bit. The discussion here is done for this Hamiltonian, which is that Hamiltonian used to study many-body localization. XXZ with on-site disorder. When this disorder strength is of the order of J, here I'm using 0.5, we have chaos. And let's start focusing on this part. What we are going to do is study the survival probability for this realistic system. So everything here is very real. Now this system can be studied experimentally. We are going to start studying initial states such as this one, where on each side the spin either points up or down in the Z direction. So this is the kind of thing experimentalists can prepare also. We are going to use initial states in the middle of the spectrum, this whole Hamiltonian. We'll do averages over initial states, averages over disorder realizations, okay? And we are going to compare these results with what we get for full random matrices. Okay, so survival probability is the Fourier transform of that energy distribution of the initial state. For full random matrices, it's a semicircle, gives us the Bessel. For realistic systems, middle of the spectrum, strong perturbation, all that, Gaussian, which gives us a Gaussian decay. So this gamma is the width of the distribution. 1 over gamma is the first important time scale. Is the time for this fast initial explosive depletion of the initial state. But if we go longer in time, what shows up for the random matrix? Power law behavior. Now it slows down. We have that exponent 3. This exponent is determined by the edges of the spectrum. In the case of realistic systems, we also get a power law behavior with exponent 2. When are we going to get manifestations of spectral correlations after that? Now, up to this point, the dynamics only looked at the shape of this distribution, the shape and the edges. It has no information about the discreteness of the spectrum. Discreteness of the spectrum comes even later. You have to give time for the evolution to resolve the discreteness of the spectrum. Once it does, and if the eigenvalues are correlated, then you get to the correlation hole. So you see, it takes a long time for that to develop. And following those steps that I mentioned to you before for full random matrices, we were able to get an expression also for these realistic systems. So the expression is very similar. What is different? Just this first part, because this first part is determined by that envelope, and the envelope is different for these two Hamiltonians. This expression here is shown with this dark line, and numerics with the red curve. So you see very good agreement. Now this is log-log. And so this is my exercise for you. If you're in the mood, check that this matches, but check not only this disordered spin system, check other systems. Like we did this also for that system with couplings between second neighbors, and you see good agreement. But again, remember, you have to do averages. And here we did that for some kind of band random matrix, and also very good agreement. Yeah, but remember to do averages, otherwise you're not going to see that whole behavior. Question?
Leah, just for the time, you have about 10 minutes, okay?
Okay, so Nicola, should I keep talking until what, 5 minutes for questions, or?
No, that's fine. I mean, no, you can talk 10 minutes and then we see. We have
okay, so I'm going to keep talking and you tell me when I should stop. Okay, so this is my exercise for you guys. Try to see whether your numerical results match this expression for realistic systems. Initial state in the middle of the spectrum, chaos, all those things that I told you before, strong perturbation. Okay, so now I got to the point where, since I have those expressions for the survival probability, I can talk about time scales. What are the different behaviors that we find along this process towards equilibration, and how long does it take for these systems to finally equilibrate? Okay. We already talked about one important time scale, which was that 1 over gamma, the one for that, the initial fast behavior. The other interesting important time scale is the time to reach the minimum of the whole, the time for the ramp to start. So when do we reach this point? When we are studying survival probability? Well, this part here is the one trying to take us down to 0. The two-level form factor, the B2, is the one bringing us up. So it's where the two meet. So how can you find this time? Study this first term asymptotically. We know we have this power law behavior with exponent 3. Study this other one at short times. So put these two in our expression, do the derivative to get to the minimum point. And what do we get? That this time here, for the minimum of the whole, for full random matrices, is just a constant. For full random matrices, it's just a constant, no information about the size of the matrix. Now let's do the same for realistic systems. It's the same game. Now this one at long times, this one at short times. What is the difference now? This one at long times, the power law is 2. This makes the whole difference. When we put these two things together, the time that we get is what I was telling Fabian, is dimension to 2/3. So the time to reach this minimum, the whole grows exponentially with the system size. Okay, so let me show you the numerics and try to explain why this difference. Yeah, so here you have survival probability for full random matrices. As I'm increasing the matrix, you see the same time here. For the realistic system, as I'm increasing the size, you see that the time is growing exponentially. Why? Well, what are we doing? we prepare the system in an initial state like this, spins pointing up or down in the z direction. This state has ahead of it an exponentially large Hilbert space. So it has an exponentially large number of other states of this kind to visit. But how is it going to do that? Step by step with its local two-body couplings. So my excitation is on site 5, then it moves to 4, then from 4 it goes to 3, step by step. An exponentially large number of states to visit. So it takes an exponentially large time to visit this whole Hilbert space. It's different from full random matrices. The matrix is completely filled. My initial state is directly coupled to everything else. So it doesn't matter the size of the matrix. This time to reach this minimum of the whole is the same. While for the realistic system, it grows, and it grows exponentially with the system size. Now comes a detail here. You don't need to use this name, okay? It's just an analogy. But we were calling this time for this state to spread out completely, for us to reach the minimum of the whole, Taulis time. And why is that? So this is the time for the initial state to spread out completely, reach the minimum of the whole. We are calling it Taulis time. Why? Taulis time in non-interacting systems, when you have a particle, it's just the time that it takes for the particle to diffuse through the sample and escape. This is real space. Here we are talking about evolution in Hilbert space, many body Hilbert space. Okay, so we are not talking about evolution in real space. Real space and Hilbert space in interacting systems is not the same. So we are calling this like a generalized kind of Taulis time, the time to completely spread in the Hilbert space. There is another reason why we call it Taulis time. In studies of non-interacting systems, localization non-interacting systems, you have the analysis in real space, but you can also have, and well, people also did analysis of spectrum, spectrum statistics, level statistics. One of the quantity studies is that one that we mentioned before, the level number variance. So as if the system is very much delocalized, falling random matrices, we are here in that log that I told you before. But as the disorder increases and the level you're killing the correlations, what you're going to see is that you stay on the GOE for a while and then it escapes. This point where the level number variance escapes is what is known as Taulis energy. This is done for non-interacting systems. And the inverse of the Taulis energy is the Taulis time. Okay, so for non-interacting systems, this analysis in level statistics and real space coincides. What we did was to do this for the interacting system and pick the point where the level number variance escapes. Well, this was actually done by Garcia first, but then we pick this energy and we compare with the time to reach the minimum of the whole. And you see that they agree. So that's another reason why we were calling that Taulis time. But this is an analysis from spectrum. This is an analysis based on Hilbert space, okay? Okay, the final time that we have is the time to finally saturate. How do we get to this one? By studying this quantity at long times. Now, this time is going to be the same no matter what we have, random matrix, realistic system. This time, you can go through the derivation, but this time is just the inverse of the mean level space. The inverse of the mean level space is the maximum, the largest possible time scale that we have in a system, is what is known as Heisenberg time. Yeah? So we reach this point of saturation at Heisenberg time for both, for full random matrices and for realistic systems. Okay, so this is something for us to worry about. I'm not going to tell you about the physical observables, no, but if you think about this time is huge. And so how can we talk about thermalization or equilibration if it takes such a long time to finally equilibrate? Yeah? But this is a result for the survival probability. We have different results for other quantities, but we can talk about it sometime if you want. Let me just tell you quickly in this 1 minute that I have left, what happens as we increase the disorder and we move away from the chaotic region and move to the localized region. So now I'm just going to flash some pictures, okay? Survival probability as we increase the disorder. Look at what we get. Something very similar to what we saw for the banded random matrices, right? The power law exponent decreasing, decreasing, decreasing. Very similar to what we saw for the banded random matrices. So this is a message. We can mimic these realistic systems to a certain extent with banded or different kinds of random matrices. And that can be very useful, okay? Last thing that I want to say. What happens to the correlation hole as we increase the disorder? Well, we are killing the hole because we are killing the correlations. No? So it's getting shallower and shallower, postponed to later and later times. This is what we are calling Thouless time, right? You don't need to use this name as well, but this time to reach the minimum of the hole, what happens to it as we increase the disorder? It increases exponentially with the disorder strength. Yeah, this is a result that was then confirmed by this work by Leo and Thomas. No, it's a work that became a bit polemic because they were asking, does many-body localization really exist? But they confirmed this result that we have. And this is a nice thing because you see, deep in the chaotic region, Heisenberg time and Thouless are very far away. As we increase the disorder, the Thouless, what we are calling Thouless, goes into the Heisenberg time. So there is an analogy here with the studies of non-interacting systems. This ratio in non-interacting systems is what people call Thouless dimensionless conductance. And what you're seeing is, as we increase the disorder, this ratio is going to go to 1. So it's when the system localizes. We did this for 16 sites only. You have to do big averages, long times, and so on. Now that you have all these lectures, that you learn with David Luizzi how to do exact diagonalization for large systems, you could check that for larger systems. Okay, so I'm going to stop here. There were many other things that I wanted to tell you about, but yeah, so I finished with this exercise. And so it's already 11:33 for me. So I can stop here for questions.
Okay, thank you very much, Leah, for this talk. So I believe we have some minutes left for questions. So please, are there some questions?
Artem.
Yes,
Yeah,
I have
go on.
a question. So kind of in all these cases that you've shown, one can sort of do the simulation and then one will see whether the kind of the Hamiltonian is close to a random matrix or not so close. But sort of, is there a way, given the Hamiltonian, to pick one of these, let's say, classes or whatever of random matrices, so like a full or a banded or whatnot, that one would expect fits to the Hamiltonian? So kind of without looking before.
Without looking before, now you can play. You can try to find which kind of matrix would mimic your results, but to know beforehand, no. You can just know the symmetries of your system, things like that, how sparse your system is. And then play with the same idea with the banded matrices. But I don't know, Arten, you may have something else in mind that I didn't get.
No, I mean, that was just what I was wondering, whether, let's say, I give you a Hamiltonian, you could tell me, oh, this is probably a random matrix, or no, this is probably like a banded.
It is always going to be a banded matrix, not a full random matrix, because our Hamiltonian is always going to be very sparse. And you can, knowing your Hamiltonian in a certain basis, try to mimic that with a random matrix. Now the random matrix will have randomness there. No? So it will be less correlated than your system if your system has only fixed values. But it's a game, and I think it can be more explored. I just showed to you one example. I think can be very similar.
Okay, thanks.
Other questions? Actually, I have a couple of questions. The first is about, so you probably know that for this typical Hamiltonian form to study the many-body localization transition in one dimension has been studied a lot, and in particular, if you look at the dynamics, when you approach from the chaotic side, when you approach the transition, there is some anomalous subdiffusion, which is found by many authors. And so, do you think there are some possible random matrix theory that could explain such anomalous dynamics?
Oh, that's an interesting question, Nicola. I don't know, but there must be. Yeah, there must be, because the same thing that I'm saying. If I can mimic my realistic system with a banded matrix, I should be able to do that. Well, this is very interesting, actually, yeah, because this is what we get with realistic system, and we got the same very similar behavior with a banded random matrix. So this is the region where you should have some kind of subdiffusion. That's actually a nice thing to try.
Okay, so this is another exercise
Yeah,
14.
exercise. There are many open questions here. Yeah.
Yeah, thank you. Maybe, okay, I see Fabien has raised his hand.
Yeah.
So I'm just giving motivations and tools, no, and then people can do them. Go on.
Sure, yeah, that's nice.
Sure. Actually, I have a question in the end. So your last exercise is actually puzzling me. I'm not sure how to think about that. So what you're saying is that both the Saulus time and the Heisenberg time, of course, they scale well exponentially with a number of sites, if you want, or of spins. And you say, well, no, that you can do larger system size. It would be great to check that, but I'm wondering, because we in principle we cannot access much larger system size at these time scales. I mean, we can. David has given lectures on larger spin chains and so on, but we don't have all the eigenstates. We have a very small, exponentially small fraction of them.
Yeah.
So
yeah, I know.
So
but we did this for 16. I think you could go for 18 or maybe 20. Yeah, but you cannot go much further. And that's the problem with this kind of analysis. But that's the problem with any study of many-body localization.
Of course, but I'm wondering if the scaling that you say actually could tell us about how many states we will need to keep in a method which doesn't have all eigenstate, but just a finite number. Typically, we can maybe save 1,000 states in the middle spectrum, but we could do 2,000, 3,000 if we needed it. So, but I'm wondering if this
then maybe I think the question could be up to which kind of behavior do I want to capture? So if you want to study just this initial behavior, then yes, you need very few states. If you want to capture also the power law behavior, maybe you need more. And I don't know how maybe you see.
I think the power law is fine. We actually
but for very okay, it's power law all the way to the whole, and that's going to be proportion to dimension to 2/3.
Yes,
to get to the power law here, yes, but at very long times.
Yeah, at long times we actually only get large time behavior in some. Well, let me see. No, because we have a finite fraction of states. So. Okay, I think that's some interesting questions.
But this is interesting what you're saying. Look, what I'm thinking. If you're able to get the power law, then you don't need to go all the way to the whole. You should be able to know where the saturation is. I don't know. Okay, to know.
But if we want to see the all to confirm the scaling of the Saulus time with respect to the Heisenberg time, we need to go to very large time.
I'm just trying to think that maybe you could. Just by following the power law, No, you cannot. Yeah, no, forget.
Well, I'm not sure.
Yeah.
Yeah, okay. Okay, thanks.
I see number 6 in this. What is this?
Okay. So are there some more comments or questions?
I think there's a question by Juan Diego.
I didn't see that. Where? Okay. Ah, sorry. Yeah, Juan Diego, please take unmute yourself if you want, and you can speak directly to Leah.
Yeah, thank you, Leah, for the presentation. I was wondering if it is possible, for example, to extract Lyapunov exponents from some of these survival probabilities evolutions or from some other quantities evolutions.
This is very nice. This is very nice one. Yes, yes. You should be able to, not from the survival probability, but look at the entropies. Yeah, the entropies that linear growth, and that's something very nice for you to check. Yeah, if if well, first, I don't know how you would get Lyapunov exponent from this system. Now you have to get a system where you have the semi-classical limit, but that linear growth of the entropy should that slope should match the sum of the positive Lyapunov exponents, the Kolmogorov-Sinai entropy.
Okay.
And this is nice. Well, the entanglement entropy or those Rényi entropies that I mentioned before. And this is a nice thing to check. And there is a work by Bianchi where he does that for systems that they're not very realistic, but he shows that this coincides with the sum of the positive Lyapunov exponent.
Could you please share the reference, perhaps?
Yes, but can you? Okay, if I don't, can you send me an email and then I send to you? But it's Bianchi. He's a guy from Penn State. Yeah,
okay. Thank you.
Nicola, you're mute.
Yeah, sorry. Yeah. All right. So I don't see any more questions. So of course, Slack is open and we can continue interaction. I think, Leah, you will probably put your PDF, your slides in the Slack channel.
Yes, I'll do that. And yeah.
So
and there were many other things that I didn't say, but
yes,
you can see in the notes.
I guess so. All right. So I will stop recording now. And